Right, so now let's look at what this implies for our balance law, okay, the final piece. Okay, let's start out with the form of the balance of linear momentum in the current configuration, okay, which is rho partial of v with respect to time plus gradient of v v equals divergence of sigma plus this. Okay, all right. Okay, now let's look first of all at this term. Okay, let's look at gradient of v, spatial gradient of v times v. Okay, now what you observe here is that even though this term is of the following form, right? We know that we can write the gradient, the spatial gradient of v as being the, remember how we wrote it originally, right? We wrote it as that f inverse, okay? And this is our spatial gradient of v, is v, okay? Now, straight away, we know that this term that I've drawn an under brace on is of second order, right? So what we're saying is that it has a second order term because we know that this thing is properly partial of v with respect to x times the inverse of 1 plus partial of u with respect to x, right? All of this v. Okay, now we can approximate this as again doing a Taylor series expansion of the inverse. Okay, we get terms of the form, the first order term of that inverse is indeed of this form, okay, plus higher order terms. Okay, what I've done is apply the Taylor series expansion to the formula for the inverse. Okay, all of this times v, all of this acting on v. All right, once again invoking our requirement that we know that this term here is essentially f dot, right, which is now partial of u dot with respect to x, right? So we are seeing now that in order to maintain only the first order terms, we should have just partial of v with respect to x, okay, times or acting on v, okay, right? Now, this term is indeed first order in the displacement gradient, okay, because this also is just partial of u dot with respect to x, okay. However, this term is not linear in the velocities anymore, okay. So we get a term that is quadratic Okay? All right? So here we have an instance of where the dynamic side of the balance of linear momentum introduces a nonlinearity in the problem. Okay? All right, and this is another aspect that we had not remarked upon previously. Okay? Again, in order to have an overall theory that is linear, and in order to have differential equations that are also linear in the primary variable, okay, this term is dropped. Okay? So what is done is we neglect partial v with respect to x times v, okay, to have linear PDEs. Okay? So where we are left then is rho partial of v with respect to t equals divergence sigma plus bf. Okay? Now, let's rewrite this bringing in f. Okay? We know that rho, the mass density in the current configuration, is rho 0 divided by determinant of f. Okay? We know that the divergence of sigma, which we write as okay, let me write it as this sort of operator. Okay, let me write it as partial of x f inverse. Okay, that gives me the spatial gradient operator, right? Dotted with sigma. Okay, in operator form. For BF, we have the body force in the reference configuration, right, divided by determinant of F. Okay? Once again, invoking our linearization of determinant F, we see that, so using once again 1 over determinant F is approximately 1 minus trace F. Okay? Where I first of all expanded the determinant and rewritten the reciprocal of 1 plus x as approximately 1 minus x. Okay, so I've got a Taylor series expansion here also and truncated it to first order terms. Okay, so using all of this, what we see is that we get 1 minus trace f rho 0 partial of v with respect to time equals. Now, same business here. We write f inverse as, sorry, these are all approximations. So is this. So is this. Sorry. Right. So we can now write this approximation as partial with respect to x. Now, for f inverse, I'm going to write it as 1 minus partial of u with respect to x. Okay, Taylor series expansion of the inverse. Okay, truncated to first order terms only. Okay, this operator acting on sigma. Okay, plus 1 minus trace f, again reduced to, restricted to first order terms only, bf. Okay, Once again, when we stare at this, we see that, well, if we were to maintain this term, then it's acting on the velocity, on the time derivative of the velocity, would again introduce nonlinearities because trace of f also involves a displacement u, which is involved in v. Okay? So this term would be nonlinear again. Okay? Give us a nonlinear PDE. Right? Same business here. Okay, and as far as this is concerned, right? While we would have a term that is we would have a term that where we would have an effect where the body force also depends upon the displacement gradient, upon the strains. Okay, so well this term is again nonlinear in the displacement gradient because we know that sigma is linear. Okay, this term is linear in the displacement gradient. Okay, so what is done is that the nonlinear effects are definitely thrown out. Okay, to maintain a linear PDE. Okay, now it is common to drop this dependence of the body force upon the displacement gradient simply because the body force is often thought of as something that's externally imposed. Okay, if we maintain this dependence, right, we maintain that term, right, that product of trace f and b and the body force, we end up having a body force which actually depends upon the solution. Okay, and just for simplicity, that is often dropped when linearized elasticity is being computed. Okay, so dropping terms that would make the partial differential equation nonlinear. Okay, and those were the first two terms, the term on the left-hand side and the first term on the right-hand side involving divergence of sigma. So dropping those nonlinear terms, right, and keeping keeping the body force constant, meaning independent okay, right? You want to keep the body force independent of the field that you're trying to solve for. Okay, that's a simplification. That's not needed. That is not needed to keep the equations linear. Okay, even if you had them, they would still be linear, but that's just a complication that is preferred to avoid. Okay, so with all of this, what one is left with then is this rho naught partial of v with respect to time equals this divergence or that operator acting on sigma through the dot product plus bf. Okay, which, recognizing that this now is just second derivative of u with respect to t, okay, gives us rho 0 reference divergence of sigma plus bf. Okay, and you recall that sigma is essentially the same as any of the other stresses for linearized elasticity, neglecting residual stresses. Okay, so this is how the balance of linear momentum also is reduced, mainly by keeping things linear. In this case, by keeping the PDE linear. Right? Otherwise, we go to nonlinear PDEs. Strictly speaking, some of those other forms which would arise are called quasi-linear, but they are definitely not linear PDEs. And there is this other simplification that it is desired to keep the body force independent of the solution. Okay? So this is what things reduce to, right? And now, of course, because all these quantities, especially if you look at the stress as being approximately equal to P or S, what you see is that it really doesn't matter whether this thing is, though we started out with the PDE defined in omega t, right? It is defined in omega t, or which is basically equivalent to omega naught. Okay, because we have no we no longer here have any mention of spatial objects, right? We no longer need to work with the current position because we are working with capital X. We could work with these stress tensors, right? We're working with this, which is defined on the reference configuration, right? And we're working with this, right? So really the difference between the current and the reference configurations is lost here. Okay? All right, so that is how our equations of linearized elasticity are obtained rigorously. Okay, so we'll stop the segment here.